Okay. Morning, everyone. Hello. Hey, mm, Okay, so we considered the chapter three before the middle term. A few sections were, some slides were considered before the exam, but let me go over them one more time so that you can review or brush up the ideas we considered in the class. And please do me one favor, okay? So during the class, if you have any question or if certain part is in doubt or it's not clear, then you should let me know, okay? You can ask during the class or you can email me and asking, say, okay, I need some more examples or I need another explanation of certain theorem or statement or whatever, okay? So if you do not understand any part of the lectures, please let me know. Okay, please email me so that I can go over that portion, okay, one more time, or I can so that I can provide some more examples. That's what I felt, okay, from the evaluation of the midterm papers. So, so if you have any question, please email me. Okay. Okay, let me go over a few slides in the chapter three, okay? And let me explain them one more time. Okay, first of all, given some matrix A, we want to consider three types of operations. Okay, the first operation is simply called interchange. Interchange operation interchanges any two rows of matrix A, or sometimes you may interchange any two columns. And in my class, I will call this first operation as interchange in, interchange operation or type 1 operation. Sometimes I need, so in that case, if I have, say, row I and row J, you interchange these two. So row J goes to the row I and row I go to the row J. Or you can interchange some column, ith column with jth column. Such operation is called interchange operation. Sometimes you multiply some non-zero value to a certain row or column. That will be called scaling operation or type 2 operation. So in the second case, given row I, you multiply some number, say C, and then this becomes your new row I. So this is a new row I is this one. The old one is multiplied by some number C. And this C cannot be zero. Because if you multiply zero to certain row, then all the entries will become zero. And you don't want to have that. Or instead of a certain row, you can redefine the column I by multiplying certain number to the existing column. Such operation will be called scaling operation or type 2 operation. In case of 3, the third one, you multiply any number to a certain row and then add it to another row. Okay, so given, say, row J, you multiply certain number and then add it to row I, and that is your new ith row, is the old one plus C times row J. And at this point, the only requirement is that this I is different from J. Okay, that will be called replacement operation. So the existing ith row is replaced by the sum of the existing ith row plus a scalar multiple of jth row. So that is the third type operation. And these operations will be called elementary row operations or elementary column operations. We have only these three types of elementary operations. So please remember this. Okay, you don't have to memorize this number type 1, type 2, type 3. Okay, but please remember there are three different types: interchange, scaling, and replacement. Okay, so those are elementary operations. For example, given A, if you interchange the first row and second row, you get B matrix. Okay. So when you interchange the first row and second row, you get B matrix. Okay. Or if you multiply 3 to the second column of A, so if you multiply 3 to the second column of A, then you get 6 to 3 0, the second column of C matrix. Okay. So when you perform interchange operation or type 1, you get B matrix. When you consider the scaling operation or type 2, you get C matrix. Okay. And in this case, when you multiply 4 to the third row of A, so you multiply 4 to the third row, and then those numbers will be added to the first row, then you get M matrix. So you consider the type 3 the replacement operation, then you get M matrix. So by performing those elementary row or column operation, we can derive a new matrices. Now, instead of considering this elementary row or column operation to a certain A matrix, we can perform those elementary operations on the identity matrix. So when you perform elementary row or column operation on the identity matrix, then the resulting matrix will be called elementary matrix. Okay, so given identity matrix, when you perform elementary row or column operation, then the resulting matrix will be called elementary matrix. Now, since there are three types of elementary row operations or elementary column operations, depending on the type of the elementary operation, the elementary matrix will be called an elementary matrix of type 1, type 2, or type 3. So if you perform the type 1 elementary operation, in other words, when you perform the interchange operation, then the resulting matrix, okay, something like this will be the type 1 elementary matrix. Okay, you obtain this by interchanging first the two rows of the identity matrix. Okay, or you may say you interchanged the first two columns of the identity matrix. Okay, but anyway, you obtain this E matrix by performing elementary operation of type 1. So this E will be called an elementary matrix or elementary matrix of type 1. And if I consider, say, if you multiply, given this identity matrix, if you multiply 3 to the second row, then you obtain 100, 030, 001. So F will be called an elementary matrix or elementary matrix of type 2. If I consider the replacement, say if I multiply 2 to the first row and then add it to the second row, then first and third rows are not changed, but when you multiply 2 to the first row, you get 200, and then if you add it to the second row becomes 210. So G will be an elementary matrix of type 3. Okay? And as I said, in case of E is obtained from the identity matrix by interchanging two rows. First the two rows are interchanged, you get E matrix. But you obtain E even when you interchange two columns of the identity matrix, right? So when you interchange two columns of the identity matrix, then you get E matrix. So this E can be obtained by interchanging first two rows or first two columns of the identity matrix. In a similar way, F can be obtained by multiplying 3 to the second row of identity, but F can be obtained by multiplying 3 to the second column of the identity matrix. And when I say G is obtained by performing a replacement operation, I mean, when you multiply 2 to the first row and then add it to the second row, you get G matrix. But when you multiply 2 to the second column of the identity matrix and then add it to the first column, you get G matrix. So elementary matrix can be obtained in two ways. You can perform an elementary row operation on the identity matrix, or you can perform an elementary column operation on the identity matrix. Then you obtain the elementary matrices, right? So EFG, such elementary matrices can be obtained in two ways, by performing elementary row operation or elementary column operation. Okay, but as I said, in our class, we will focus on elementary row operations. Even though we can derive some elementary matrix from by performing elementary column operation, we will focus on elementary row operations. Okay. And theorem 3.1 says, okay, so given A matrix, B is obtained by interchanging first the two rows of the A matrix. You get, that's how we get B matrix, right? So let me go over. So B is obtained from A matrix by interchanging first the two rows of A matrix, right? Then, what if I perform the same elementary operation on the identity matrix? Given 3 by 3 identity matrix, if I interchange first the two rows of the identity matrix, then what is the resulting elementary matrix? The resulting elementary matrix will be 0, 1, 0, 1, 0, 0, 0, 0, 1. So this E is an elementary matrix corresponding to that specific elementary row operation. Now please check that this B can be obtained by multiplying this E to A matrix. Okay. So B is obtained in two ways: by interchanging the first two rows in A matrix. Okay. Or, so if I perform this interchange operation, you get B matrix. Or, instead of interchanging two rows in A matrix, you can interchange two rows in identity matrix to get the corresponding elementary matrix E. Okay, and then when you pre-multiply E, when you perform a row operation, then this resulting matrix, the resulting elementary matrix, will be pre-multiplied to the given matrix. So given A matrix, when you multiply E from the left, then you can check that this product will be the same as B matrix. That is one very special property of an elementary matrix. Okay? Now, in case of C matrix, we obtained C from A by multiplying 3 to the second column of A matrix. Okay. Now, in case of a column matrix, we need to think of a 4 by 4 matrix. And then if I multiply this 3 to the second column of the identity matrix, then the corresponding elementary matrix will be 1, 0, 0, 0, 0, 3, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And then if you multiply A with G matrix, you get C matrix. Okay, so here C is obtained in two ways. First, by multiplying 3 to the second column of A matrix. Or you can derive the corresponding elementary matrix G, and then if you multiply G to A from the right, then you get C matrix. And in case of M, we perform the type 3 operation. We multiply the 4 to the third row of A and then add it to the first row. Now, given the identity matrix of 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, if I multiply yeah, if I multiply 4 to the third row of the identity matrix and then add it to the first row, what do I get? Then we get 1, 0, 4, 0, 1, 0, 0, 0, 1. And then if you multiply H to A matrix, you get M matrix. So you can directly performing this third type row operation, or you can perform the third type row operation on the identity matrix to derive H matrix. And then if you multiply H to A from the left, you get M matrix. So that is a very special property of the elementary matrix. So here is the theorem. Suppose that I have any matrix, okay? Any matrix. And then you obtained some matrix, say B, by performing some elementary row operation. Then when you perform the same elementary row operation on the identity matrix, then you get some elementary matrix E. So E is obtained from the identity matrix by performing the same elementary row operation on the identity matrix. And then if you multiply E to A from the left, then you get B matrix. In case of a column operation, you consider the identity matrix and then perform the same column operation, and then you need to multiply the corresponding elementary matrix from the right. Then you get B matrix. So this is a very special property. So from now on, as I said, excuse me, given some A matrix, when I perform some row operations to get certain matrix, say C, then all the matrices in between can be obtained by multiplying appropriate elementary matrices. But anyway, this is a very important property of an elementary matrix. So let me go over one more time. Okay. So given A, you obtain B by performing some elementary row operation. Okay. Then you perform the same elementary row operation on the identity matrix to get E matrix. Once you get this E, you multiply E to A from the left. Then you get B matrix. If you performed a column operation, then you perform the same column operation on the identity matrix, and then you multiply the elementary matrix from the right. Okay? Now, given some m by m matrix, so if I have on m by n matrix A, elementary matrix is obtained from the identity matrix. So elementary matrix will be a square matrix. If your square matrix E is multiplied from the left, then this matrix must be an m by m matrix, right? If you multiply the certain matrix from the right, the matrix must be an n by n matrix. So if you perform an elementary row operation, then you will perform the same elementary row operation on the m by m identity matrix, so that you obtain an m by m matrix, so, so that you can multiply that matrix from the left, right? If you perform a column operation, then you must multiply an elementary matrix from the right. So the matrix must be an n by n matrix. So you start with an n by n identity matrix, and then you perform certain column operation. Then resulting elementary matrix will be multiplied to the given matrix from the right. So that's what we considered before the exam, right? So here is another example. Given A matrix, as I said, B is obtained from A by interchanging first two rows of A matrix. So B can be obtained directly from A by interchanging two rows in A matrix. Then you get B matrix. Or or you can perform the same interchange operation on the identity matrix to derive an elementary matrix E, and then when you multiply E to A, then you get B matrix. So B can be obtained in two ways, okay? By interchanging first two rows in A matrix. So you can perform the elementary row operation directly on A matrix, or you can perform the row operation on the identity matrix, not on A matrix, to derive this E matrix, some elementary matrix. And then when you multiply E to A, you get B matrix. And as I said, another very important property of the elementary matrix is this elementary row operation or column operation is reversible. In other words, we can undo those operations. Meaning we can go back to the previous stage, right? And as I said, in case of the interchange operation, what is the operation which avoid the previous interchange operation? You can interchange one more time, right? If you interchange first the two rows in A matrix, when you re-interchange those two, you go back to the previous stage, right? In other words, given A matrix, if I interchange first the two rows of A to get B matrix, if I interchange first the two rows of A, B matrix, you get A matrix, right? So that means B is obtained from A by interchanging two rows in A matrix. Now, as I said, given B matrix, if I perform interchange operation, that means that is equivalent to multiplying E to B matrix, you get A matrix. In other words, given A, when I multiply E to A, you get B matrix. This is B. Given B, if I multiply E one more time, you go back to A matrix. So that means E times E will be the identity matrix. That means the inverse of E will be E matrix. So the E matrix is invertible. And so the inverse of E is E itself, right? Given A matrix, if I multiplied 3 to the second column, we obtain C matrix. The C was 1, 2, 4, 6, 3, 0, 3, negative 1, 1, 4, 3, 2. And in case of C, we obtain C from A by multiplying G matrix in my previous notation. And G is an elementary matrix obtained from the identity matrix, right? You perform the same column operation. I mean, multiplication by 3 to the identity matrix. And then if you multiply G to A, you get C matrix, right? Now, given this G matrix, if I define G, how can I go back to A matrix from C? You can go back to A if I multiply 1/3 to my second column of C matrix, right? So if I multiply 1/3 to the C matrix, you go back to A matrix, right? But what does that mean? I mean, given the identity matrix, if I consider such elementary column operation, then we can think of some G star, and then the corresponding elementary matrix will be 1, 0, 0, 0, 1/3, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And given this C matrix, if I multiply G star, you get A matrix, as we know. And C was A times G. And if I multiply G star, you get A matrix. So that means this G star multiplication will give you the identity matrix. That means the inverse of G will be G star. Right? So, in case of scaling operation, if I consider this G star, now how do I obtain this G star matrix? The scaling factor was 3, and in case of G star, the inverse, I need to replace this scaling factor with its reciprocal, 1/3. And considering the reciprocal of a number, reciprocal of a scaling factor is not a problem, because when we consider the scaling operation, the type 2 operation, we multiply a non-zero value. So the scaling factor is not 0. So we can always think of the reciprocal of the scaling factor. So that means given any elementary matrix corresponding to the column up the scaling operation, we can always think of something like G star, which is an inverse, right? So this is G, okay? So in case of E, the inverse of E was E itself, meaning the inverse of type 1 elementary matrix is the matrix itself. Okay? Meaning the inverse is also type 1 elementary matrix. In case of G, the type 2 elementary matrix, G star is the inverse, and this G star can be always found, and this G star is also type 2 elementary matrix. Only the scaling factor is 1/3, not 3. And in case of the third type, we previously considered the replacement. We multiplied 4 to the first row and third row, and then added to the first row to get M matrix. You remember that? And in case of M, we obtained from A by multiplying H matrix, and H is obtained from the identity matrix by multiplying 4 to the third row and then add it to the first row. Right? Now, from M matrix, then how can, so what is M? M is, say, 17, 2, and 7, and 12. 2, negative 2, 1, negative 1, 3, 4, 0, 1, 2 matrix. So from A, we could find M matrix. Now, and this M can be obtained from A by multiplying A and H in that order. Now, how can I go back to A matrix? So, given A, I multiply the 4 to the third row and then add it to the first row. Given the third row in M, if I multiply negative 4 to the third row and then add it to the first row, you go back to A matrix, right? So given H matrix, if I consider H star corresponding to this specific row operation, so instead of multiplying 4 to the third row, you multiply negative 4 to the third row and then add it to the first row, then you get this H star matrix. And then if, sorry, H times A is M. Sorry about that. Now, given this, I can go back to A from M by multiplying H star to M matrix, which means H star times H times A will be A matrix, meaning H star times H will be the identity matrix. So H star is the inverse of H matrix. So H star, some elementary matrix corresponding to the replacement or type 3 operation, and that operation only has the negation of this number 4 which we used in H matrix. Okay. So given this H, we could find H star, and that is also type 3 elementary matrix. Okay. And E is the inverse of E, and that is type 1 elementary matrix. And G star is type 2 elementary matrix. So the theorem 3.2 says elementary matrices are invertible. In other words, elementary row operation is reversible so that we can undo those elementary column or row operations. And the inverse of an elementary matrix is also an elementary matrix of same type, right? So that's what we could observe in from the example, or you can check the proof. We already considered those previously, and we already mentioned this example. This is the exercise problems, and you can just check this yourself. I already considered this previously. So that's what we considered in section 1. We considered elementary row or column operation and the effect of performing elementary row operation is the same as multiplying the corresponding elementary matrix to the given matrix. And more than that, all these elementary matrices are invertible. Okay. So that's what we considered in section 1. Then in section 2, we considered the rank of a matrix. Now, previously, we considered the rank of a linear transformation, right? Now, given a matrix, any m by m matrix, we define its rank with by the rank of linear transformation L sub A. L sub A was left multiplication operation, meaning given any x vector in Fn, x is mapped to A times x in Fm space. Okay. So we can consider such linear transformation and the rank of okay. What was the meaning of the rank of this linear transformation? How do we define the rank of a linear transformation? This was the dimension of the range of this mapping. Okay. Given this t, I'm sorry, we have L sub A. Given this linear transformation L sub A, we can find the range, the collection of, so the range means the collection of A times x vector when you consider all the x vectors in the domain. So this is the range. And then if you consider its dimension, that's what I mean by the rank of this L sub A transformation. Okay? And we define the rank of a matrix. So the rank of a matrix by this, okay? Now, previously, we could consider this matrix. What is this? What does this notation imply? This T is a linear transformation. So here, T is a linear transformation from V to W. And beta is a basis of V space, the domain. Gamma is a basis of W space. So beta is the basis of the domain, and gamma is the basis of the codomain, and T is a linear mapping from V to W. Then, then when beta consists of, say, V1, V2, up to Vn, this T will map each of vector in this basis. Given these vectors in W, we can find the coordinate of these vectors with respect to gamma. Then those are some m tuples of numbers, some vectors with m entries. When I construct a matrix with those column vectors, that's what I mean by the matrix representing this linear transformation T with respect to beta and gamma. Okay, this is the matrix obtained in this way. Then, then based on the exercise problem, we can easily derive one simple fact. The rank of this linear transformation will be the same as the rank of this matrix. So if I call this matrix by A, then that will be the rank of L sub A. Okay. So that is the same as rank of A matrix, and that will be the same as rank of T. Okay. Please note that when I say rank of T, then that, as I said, that is representing the range of T within W. So that is the range of T in W space. And then you consider its dimension. Okay. When I say rank of L sub A, okay, please remember that the L sub A is a mapping from Rn to Rm space. So the range of L sub A is a subset of R sub R to the Rm space. Okay? Range of T is a subset of W space. So those two are different. Okay? Let me repeat one more time. So here, T is a mapping from V to W. And this is a matrix from Rn to Rm matrix. So the if I call this guy by A for simplicity, then L sub A is a mapping from Rn to Rm space. Okay, so the rank of A equals rank of T. So when I say rank of T, then that means, okay, it means the dimension of the range of T mapping. So that's what I mean by rank of T. Okay, but the definition of rank of a matrix was given by rank of L sub A transformation. And that means dimension of the range of L sub A mapping. And range of T is included in, so that is within, that is contained. So range of T is contained in W space. However, range of L sub A is contained in Rm space. So V and W can be any vector spaces like P3 space or the space of matrices or functions, whatever. In case of L sub A, it is a mapping from Rn to Rm. So the spaces are different. I mean, the ranges of these two mappings are in two different spaces. So usually rank of T is a little bit difficult to find relatively, I mean, compared to rank of L sub A. But anyway, that's what we mean by theorem 3.3. Rank of T equals rank of this matrix. Okay? And rank of a matrix is defined in the above by the rank of linear transformation L sub A. So we have this situation. That is the summary of the previous slide. Okay. So if I want to find rank of a matrix, by definition, the definition says we need to consider this L sub A transformation, find its range, and consider its dimension. Okay. The next theorem simplifies that part. It's not this one, the one which we will see in a moment. So before we consider some generalized statement, the theorem 3.4 says, given any matrix, if you multiply on invertible matrices to A from the left or from the right, the rank is not changed. Okay? The rank does not change when you multiply on invertible matrix from the left or from the right. One of the simple element, the invertible matrices are elementary matrices. Okay, so here in this theorem, we already proved this theorem, right? But I'm just brushing up this. So if P and Q are invertible matrices, then when you multiply those invertible matrices to A from the left or from the right, the rank is not changed. Okay? So one of the examples for the invertible matrices are elementary matrices. So let me combine these two. So given A matrix, if I multiply on elementary matrix from the left or from the right, the rank is not changed, right? So let me, so So when an elementary matrix is multiplied to A from the left or from the right, the rank is unchanged, right? So this is an example of the theorem, right? Now, what does this imply? The multiplication, some elementary matrix is multiplied to A from the left. That means when an elementary row operation is performed on A matrix, or if you multiply such elementary matrix from the right, that means some elementary column operation is performed on A, the rank is unchanged. That is the result of the theorem, right? So when I consider this theorem 4.4, okay, 3.4, so the theorem says when you multiply on any invertible matrix, the rank is not changed. And as a special case, an elementary matrix is an invertible. So that theorem 3.4 says when I multiply an elementary matrix to any matrix, the rank is not changed. In other words, but the multiplication by an elementary matrix is equivalent to performing the elementary row or column operation. So when elementary operation is performed on a matrix, the rank is not changed. That is the claim of theorem 3.4. Okay, so that is the meaning of this theorem. So as I said, elementary matrices are invertible. So if you perform elementary row or column operations on certain matrix, the rank is not changed. That's what I already mentioned. Now, theorem 3.5, which we already mentioned, what is this? The rank of any matrix, okay, equals the rank. Okay, here, when I say the rank of a matrix, by definition, it was defined by the rank of left multiplication operation, and rank of any linear transformation considers the dimension of the range of that mapping, right? That was the definition. But considering the identifying the dimension of the range is not that simple. Okay. So theorem 3.5 introduces a very simple result. Given a matrix, what you can count is the number of independent columns. So the rank of any matrix will be the maximum number of linearly independent columns. Then, then So we already considered the proof. So please check the previous video recording for the proof, and let me consider the meaning of this theorem. So given A, so if A is on m by n matrix, then we can think of left multiplication L sub A, this mapping from Rn to Rm matrix. I'm sorry, Fn or Fn to Fm. There might be. So from Fn to Fm, this mapping. Okay. And rank of A was defined by rank of a linear transformation L sub A. And rank of a linear transformation was defined by the dimension of the range of this L sub A mapping. So that's how so this was defined by the rank of linear transformation. This is specific linear transformation. And rank of a linear transformation was defined by the dimension of the range of this mapping. Okay. But the previous theorem, theorem 3.5, shows that, okay, instead of considering this rank, the rank of a linear transformation, we can directly identify the rank from the matrix itself. The theorem 3.5 claims that what you can do is you can just count the number of independent columns. That will be the rank of a matrix. So this number, the number of independent columns, will be the rank of L sub A transformation, or that will be the range of L sub A space. But what is the range of L sub A? What is this? The range is, as I said, the collection of A times X vector when X varies within the domain. What does A times X represent? A times X. What is this? If A is an m by m matrix with n columns, A1, A2, up to AN columns, and if X consists of X1 up to Xn numbers, then what does A times X represent? A times X is just X1, A1 plus X2, A2 up to Xn, AN. So this is a linear combination of the columns in A matrix using the entries in X as the weights of the linear combination, right? So this range is the collection of all the possible linear combinations of the columns in A matrix. So that will be the space generated by the columns in A matrix. Okay, so this is the space generated by the columns in A matrix. Given this space, you consider its dimension, or as I said, the space is the collection of, excuse me, the set of all linear combinations of the columns in A matrix. So if you consider that space and if you want to find the dimension, that will be the same as the dimension of the space generated by the columns in A, or mathematically that is the collection of all the A times X vector. That is, anyway, those are representing the range of this linear transformation L sub A, okay? And that defines the rank of a matrix. And the theorem says that rank, all these dimensions will be just representing the number of independent columns in a matrix. Okay? So that is the meaning of this theorem 3.5. Okay, so let me go back a few slides. So here in this slide, if I have a linear transformation T from V to W, then you can directly find the range of T and then you can count its dimension. That will be the rank of T. Okay, but the theorem says this rank of T will be the same as rank of A if I define this matrix by A. Okay, and for this A, what you can do now is that will be the number of independent columns in A matrix. So you can just count the number of independent columns. That will be the rank of this matrix. Okay, so you need to understand the meaning of each statement. So in theorem 3.3 connects the rank of a linear transformation and rank of a matrix. Okay, and theorem 3.4 says, okay, when you perform elementary row operation or column operation, the rank is preserved. So this corollary is more important. When you perform elementary operation, the rank is preserved. Theorem 3.5 says the rank of a matrix is related with the number of independent columns. So the rank of a matrix just counts the number of independent columns in a matrix. And in theory, that will represent dimension of this space generated by the columns in A but that is actually equivalent to the space of linear combinations of the columns in A matrix. If you consider the collection of all those linear combinations, that will generate certain space. Symbolically, this is just the A times X vectors. So if you consider those A times X vectors, okay, the dimension of those spaces will be just the number of independent columns in A matrix. So those are the meaning of these statements, theorems. So please read this carefully. Okay. So in example 1, given this matrix A, as you can see, the third column is the sum of first two columns, right? So the third column is redundant. First two columns are linearly independent because the first column is not a multiple of the second column, and the second column is not a multiple of the first column. So the first two columns are linearly independent. But the third one, okay, so do you follow me about this? So the column 1 is not a multiple of column 2, and column 2 is not a multiple of column 1. So these two statements show that column 1 and 2 are linearly independent. But column 1 plus column 2 will give you column 3. So the column 1, 2, 3, if I consider all three columns, they are linearly dependent. So, so the maximum number of linearly independent columns in A matrix will be 2. So this 2 is the dimension of the range of this mapping, L sub A. Okay. So that is the collection of all the A times X vector when X varies within the R3 space. And previously, the collection of the set of all linear combinations of the columns, those space was called the span of the columns in A matrix. So if I consider its dimension, that will be the number of independent columns in A matrix. So rank of A in that sense is 2. In example 2, given A, if I subtract the first row of A from row 2 and row 3, you get this matrix. So by performing two elementary row operations, you get this second matrix. Then, since the elementary matrix is performed, if I call this guy by A1, then rank of A and rank of A1 will be the same because I performed elementary row operations. Now, if I subtract the first column from the second column and subtract the first column from the third column, you obtain this matrix. Let me call this guy as A2. Then, since I performed some elementary column operations, the rank of A1 and rank of A2 will be the same. So A1, A2, these all three have the same ranks. Now, in case of A2, the first column is independent from the others, but third column can be obtained from the second column by considering So by multiplying negative 1 to the second column. So that means the number of independent columns will be 2. So the rank of A2 is 2, and that will be the rank of A1 and rank of A. Okay? Anyway, thank you for listening, and let's call it a day here, and see you next time.